The inside of a jet engine runs at around 1,500 degrees Celsius. That's hotter than lava. That's hot enough to melt most metals on Earth. And yet, the metal blades spinning inside that engine have a melting point of around 1,280 degrees, so the engine is literally running over 200 degrees hotter than the blades can theoretically survive. So, why doesn't the whole thing just turn into a puddle mid-flight? But why does it happen? The operating speed of metal is 200 degrees hotter than the melting point of metal itself. Before we get to the melting problem, let's quickly cover how a jet engine actually works. At the front, there's a huge spinning fan, the one you can see when you're boarding a plane. That fan sucks in a massive amount of air, about 1.3 tons every single second. Some of that air gets squeezed down by a series of compressors, basically getting squashed tighter and tighter until it's around 50 times normal air pressure. And just from being compressed like that, the air heats up to about 600 degrees. Then fuel gets sprayed in and ignited. That explosion pushes the temperature up to around 1,500 degrees Celsius. Now that super hot gas wants to expand and escape, and on its way out, it has to push past rows of spinning metal blades, the turbine blades. Those blades spin at over 12,000 revolutions per minute, and that spinning power drives everything else in the engine. The compressors, the big fan at the front, all of it. It's almost counterintuitive. The real action is happening in the back, and it's driving everything in the front. Now here's where it gets brutal. Those turbine blades are sitting in a 1,500 degree stream of gas. They're also spinning so fast that each blade is being pulled outward with a force equal to the weight of about 20 tons. That's like two double-decker buses yanking on a single blade while it's glowing hot. Along with that, the hot oxygen wants to chemically react with the metal and eat it away, and the air being sucked in from outside carries dust, sand, and particles that slowly grind away at everything inside. So you need a material that can handle insane heat, enormous stress, chemical attack, and constant abrasion, all at the same time, for tens of thousands of flight hours. The answer is a special family of metals called nickel superalloys, and what makes them remarkable starts at the atomic level. Here's a simple way to think about it. Inside any metal, there are tiny imperfections in the atomic structure. When you apply heat or pressure, those imperfections start moving, and the metal slowly bends and deforms over time. It's called creep, and it's what causes metals to fail. In nickel superalloys, engineers added a tiny bit of aluminum, and something remarkable happens. The atoms self-organize into microscopic cube-shaped structures that act like tiny roadblocks. They physically stop those imperfections from moving. As temperature rises, these roadblocks actually get stronger for a while. Most metals get weaker when you heat them. These get stronger. It's like the heat activates them. Modern turbine blade alloys contain up to 10 different elements, each added for a very specific reason. Chromium protects against rust and corrosion. Rhenium, one of the rarest metals on Earth, slows down atomic movement at extreme temperatures. In fact, more than 80% of all the rhenium mined in the entire world ends up right here in jet engine turbine blades. But even with all of that, there was still a massive problem. All metals are made up of tiny crystals, millions of them packed together, kind of like grains inside a sugar cube. And the boundaries where those crystals meet? That's where metals crack and fail under stress. Under the extreme forces inside a spinning turbine, those grain boundaries are like fault lines. The crystals start to slide past each other, the blade slowly deforms, and eventually, it fails. So engineers came up with something remarkable. They figured out how to grow each turbine blade as a single continuous crystal. No grain boundaries, no fault lines. One perfectly aligned structure running from the base of the blade all the way to the tip. The process is genuinely fascinating. They pour molten metal into a ceramic mold, then slowly cool it in a very controlled way. At the bottom of the mold, there's a tiny spiral-shaped passage called a pigtail. As the crystal grows upward through that spiral, all the competing crystals get choked out until only one survives and grows up through the entire blade. What you end up with is a blade that contains more atoms than there are stars in the observable universe, and every single one of those atoms is locked into the exact same crystal pattern. Single crystal blades last up to 9 times longer under heat stress than regular metal blades. That's not a small improvement. That completely changed what jet engines could do, but even a perfect single crystal blade would still melt at 1,500 degrees. So there are 2 final tricks. First, the blade is hollow. Tiny channels run through the inside, and cooler air gets pumped through them constantly, acting like a cool invisible shield around the blade. Second, every blade is coated with a ceramic layer. It's only about 1/4 of a millimeter thick, but that tiny ceramic coating keeps the metal underneath it up to 170 degrees cooler than it would otherwise be. That's the final barrier between the blade and the heat trying to destroy it. So when you put it all together, a superalloy engineered at the atomic level, grown as a single perfect crystal with internal cooling channels and a ceramic coating, you get a blade that can survive conditions that should, by all rights, be impossible. And right now, there are around 10,000 planes in the sky, each one powered by engines running hotter than their own melting point. Every single flight. Next time you're on a plane, just think about that. A quarter millimeter of ceramic coating and some very clever atomic engineering is what's standing between you and 1,500 degrees. These things really shouldn't work, and yet they do.